Hi everyone, welcome to part 2 on our video lecture for section 10.5 on the comparison test. In part 1 of this video lecture, we learned a new test called the direct comparison test. Now in part 2, we'll learn about another comparison test which is known as the limit comparison test. If you recall, at the end of our part 1 video, we encountered a problem where the direct comparison test was inconclusive. Lucky for us, the limit comparison test will give us an alternative approach that may work for those inconclusive cases. So let's go ahead and begin here with the limit comparison test. So suppose that we have a sub n to be greater than 0 and b sub n to be greater than 0 for all n, which again, this means that we're only dealing with positive terms, and the limit as n approaches infinity for a sub n over b sub n is equals to L, where L is, and this is important, a positive and finite number. If that's the case, then the two series, as n goes from 1 to infinity for a sub n, and as m goes from 1 to infinity for b sub m, then they either both converge or they both diverge. So in other words, they behave the same. This test will be similar to the direct comparison test in the sense that we're going to need to select a comparison series. Now this one here will be a known series that we can use to compare our series. Once we've done that, we'll set up the limit as n goes to infinity for the a sub n and the b sub n terms. Now, as long as the limit is finite and positive, so that means that we don't want a zero there, then the test will be conclusive. So what this test will tell us is that, again, both series will behave the same. So if you know that the comparison one was converging, then you know that the other one will converge as well. And if the case for divergence, it's going to be the same thing. If the comparison series diverges, then the series of interest will also diverge. So let's go ahead and take a look at a couple of examples so we can get more familiar with the concept. Okay, so for our first example, we have the sum as n goes from 1 to infinity for 1 over 2 raised to the n minus 1. Okay, so just as with the direct comparison test, let's see if we can come up with a nice series to compare this one to. Well, for this particular example, since I'm saying that I'm dividing by a 1 over 2n, I'm going to say that this series compares to the series as n goes from 1 to infinity for 1 over 2 to the n. Now we know that this one here is a geometric series, so we know that this one here will converge. And again, we know this because the R value, the common ratio, was 1/2. Okay, so now that we've figured out our series to converge to, and we know that it converges, let's go ahead and use the limit comparison test. Now we're going to be taking the limit as n approaches infinity of our a sub n over b sub n. Now at this point we have a little bit of freedom. Which series do we want to be on the numerator? Which one do we want to be on the denominator? Typically I pick my original series to be my a sub n and just put that in the numerator. So I'm going to have 1 over 2 to the n minus 1 divided by our comparison series 1 over 2 to the n. Okay, now for this one here, doing a little bit of simplification for the complex fraction, we're going to get the limit as n approaches infinity for 2 to the n divided by 2 to the n minus 1. Now, at this point, we can go ahead and evaluate the limit directly, but we would see that we would be getting an infinity over an infinity, which is an indeterminate form, so it means that we can go ahead and use L'Hopital's rule. So for this example, I'm going to go ahead and use L'Hopital's rule to get the limit as n approaches infinity for the ln of 2 times 2 to the n divided by the ln of 2 times 2 to the n. Now you get to see here that essentially everything is canceling. So we just have the limit as n approaches infinity for 1, which is just 1. Now, is this a good value to get? Well, this one here is positive finite, so it works. That means that the limit comparison test is telling us that either both series will converge or both diverge. But since the comparison series was converging here, we know that by the limit comparison test, our original series, as n goes from 1 to infinity for 1 over 2 to the n minus 1, also converges. Alrighty, so this is the idea here. As you can see, it is very similar to the direct comparison test. Okay, let's take a look at another example. Alright, so for our next example, we have here the limit as n goes from 1 to infinity for 7 to the n divided by 3 to the n plus 9n minus 3. Okay, so taking a look at this one, which one will be a nice series to compare it to? Well, you probably guessed it right. This series can be compared to the series as n goes from 1 to infinity for 7 to the n over 3 to the n, which we know here that this one is also a geometric series, but compared to the other one, this one will actually diverge because you get to see here that this one has an R value of 7/3, which is greater than or equals to 1. Alright, so this one is a geometric series that diverges. Okay, so now that we have established the comparison series and figuring out its behavior, let's go ahead and find out our limit. So we're going to have here the limit as n goes to infinity, 4 7 to the n all over 3 to the n plus 9n minus 3, and that is divided by 7 to the n over 3 to the n. Alrighty, so at this point for this one, I am going to go ahead and multiply by the reciprocal of the denominator. So multiply here by a 3 to the n over 7 to the n, both top and bottom. What are we going to get? Well, a couple of things are going to cancel. For starters, we don't have this denominator anymore, and we also get to cancel the 7 to the n. So we're left with the following. The limit as n goes to infinity for 3 to the n divided by 3 to the n plus 9n minus 3. Okay, now for this one, again, if we go ahead and evaluate the limit directly and let n get arbitrarily large, then we would be having infinity over infinity, which is an indeterminate form, and we can go ahead and use L'Hopital's rule. But I already used L'Hopital's rule in the previous example, so for this one, I'm going to show you a different approach. You might remember this approach whenever we were finding horizontal asymptotes. We said that to find a horizontal asymptote, we needed to divide everything by the term with the highest power in the denominator. Now in this case, the term with the highest power, or the term that is growing the fastest, is 3 to the n. So one thing that we can do is divide everything by 3 to the n. Once we do that, a couple of things are going to cancel. This one becomes 1. So this is becoming 1. However, as we let n go to infinity, then we know that the 3 to the n is growing much faster than 9 to the n. So this one's going to go to 0, and this one is going to go to 0. So once more, it seems like our limit here is 1. Now, is that a good value? Yes, it is. This one here is positive and finite, so we can go ahead and use the limit comparison test. Okay, so now, by the limit comparison test, since our comparison series, the 7 to the n over 3 to the n, was diverging, then our original series will also be diverging. Okay, and there we go. That's it for this problem. Now, I'll mention one more thing. Now, for this example, to figure out the limit, I divided everything by 3 to the n, but to be honest, you could have also just looked at the n behavior. So notice that the highest powers on both numerator and denominator for this series here was 3 to the n. So this one here, 3 to the n divided by 3 to the n, was equals to 1. So there we go. That's another way of figuring out the limit. Just getting the ratio of the 3 to the n over 3 to the n. Okay, now let's get more practice. Let's take a look at another problem. Alrighty, so for this next problem here we have what is the series as n goes from 2 to infinity for 1 over ln of n. Alright, so now this series looks a little bit trickier because, well, we really haven't seen a series with an ln, so what can we compare it to? Well, I'm going to take a look at the behavior for this one. We have 1 over the ln of n. So, in essence, we have 1 over a variable, something that is changing. So, what I'm thinking here to choose as a comparison series is the following. We can compare it to the series as n goes from 2 to infinity for 1 over n. And again, remember this one here was a special series. This one was a harmonic series. And we also encountered this series before. We evaluated, or we found out whether the series was diverging or converging using the integral test, but we can also use the p-series test. So this one here, if it has a p-value of 1, then this one is diverging. Now, this one here will be a very useful series to compare other series to. So whenever you're at a loss or maybe a little bit confused on what series to compare it to, if you notice that you have a 1 over n or 1 over a variable or 1 over something that is changing, I always suggest using the harmonic series as a comparison. Okay, so let's go ahead and take a look at the limit comparison test, because we know that this one here is diverging. So we're going to go ahead and take the limit as n goes to infinity. So we're going to have the limit as n goes to infinity for 1 over the ln of n over 1 over n. So rewriting this one, we're going to get the limit as n goes to infinity for n over the ln of n. Now this one here, we're going to be getting an infinity over infinity, so I'm going to go ahead and use L'Hopital's rule. So taking the derivative of the top, we're going to get a 1. Taking the derivative of the bottom, we're going to get a 1 over n. And we're taking the limit as n goes to infinity. Now, the thing that happens here, though, is if you have 1 over n, we can go ahead and easily rewrite this one as the limit as n approaches infinity for n, which now we are in a little bit of trouble because in this case, the limit is infinity, so the limit does not exist. So for this particular problem, the limit comparison test isn't conclusive. It doesn't work. Because again, we want our limit to be positive and finite. Okay, now at this point, since we have seen two comparison tests, I'm going to go ahead and refer back to the direct comparison test. Okay, so as a refresher for the direct comparison test, remember once we figure out your series that you're comparing, we can go ahead and figure out which one of the series, or the general terms, is bigger. Is 1 over the ln of n bigger than 1 over n? Which one is bigger? Well, if you're a little bit unsure, you can always plug in values into your calculator, but in this case, the 1 over the ln of n is actually greater. Okay, so what does this mean? Well, we know that the series 1 over n was diverging, and it was the smallest one. So then we know that the larger one also diverges due to the direct comparison test. So we can go ahead and say that the series 1 over the ln of n diverges by the direct comparison test. Okay, so let's go ahead and try one more problem. So this next problem, again, looks a little bit confusing. We have the series as n goes from 1 to infinity for the sine of 1 over n. We really haven't seen that many trig functions when we're comparing our series. So what can we do? Which one would be a good series to compare this one to? Now again, this is the sine of 1 over n, not the sine of 1 over n or anything like that. However, because I do see some n in the denominator, to me that's a hint that I could probably compare it to the harmonic series. So I'm going to go ahead and compare it to the series for 1 over n. And again, we know that this one diverges. Okay, so let's go ahead and use the limit comparison test. So we're going to take the limit as n goes to infinity for the sine of 1 over n divided by 1 over n. Okay, now for this one here, I'm not going to go ahead and multiply by I'm not going to go ahead and get rid of the complex fraction. What I'm going to be doing instead here is recognize that I have a 1 over n inside the sign and a 1 over n in the denominator. So I'm going to go ahead and let u equals to a 1 over n. Okay, now what's happening to u as n goes to infinity? Well, as n goes to infinity, then the u is going to go to 0. So I'm going to go ahead and make a switch here on my limits. Rather than dealing with n's, I'm going to switch to u's and figure out what's the behavior for u. Well, we already figured out the behavior, but I'm going to use that behavior to rewrite the limit. So this one here is the same thing as the limit as u goes to 0 for the sine of u over u. Okay, so now we can go ahead and work with this limit. Now again, if you plug in 0 for u, we have 0 over 0, which is an indeterminate form, and we can go ahead and use L'Hopital's rule. So it's going to give us then the limit as u goes to 0 for the derivative of sine is a cosine of u all over 1. Now what is the cosine of 0? The cosine of 0 is just 1. Okay, so very good. We're getting a value for the limit here, which is positive and finite. So it looks like our limit comparison test is going to work. So let's see. Then if we knew that the 1 over n series was diverging, then by the limit comparison test, the series as n goes from 1 to infinity for the sine of 1 over n also diverges. Okay, so this is it for this video, guys. I know I left you hanging with this one. If you're interested for this one, I'll probably put it as a discussion board problem, so you guys can figure out if this one will be diverging or converging. Now, going back to the last two examples that we did though, I want you to note that comparing a series to 1 over n is very common. It's something that you can go ahead and take advantage whenever you notice that, again, you have 1 over some variable or you see a 1 over n somewhere in there. Choosing the harmonic series can guide you to an answer. Alrighty guys, so this is it for this recording. I will see you in the next one. See ya.